kind introduction. So it's a pleasure to outline today's meeting. So we will tackle first the introduction, then we will give you some insights in the different types of definition of primary energy, as well as the different accounting methods which are applied and out there for electricity and steam. And we will then show some applications of the different accounting methods in practice. And for sure, we will summarize the presentation with some conclusions. And as Hans already said, this part is the first part of a series of two. So in 2 weeks, we have then the policy implications of the different accounting methods. So yeah, that brings me already to the first question I have. So Alex, what is primary energy, and does the accounting matter? And if yes, why?
Yeah, thank you, Oliver. Yeah, primary energy accounting, if you look at the first glance, it does not sound very exciting topic. But we believe that it is really an important topic because if you think about this left figure here, it's the projected energy consumption of the European Union, which was done in 2007, and later on we formulated a kind of energy efficiency directive where a 20% saving target was formulated, and you can see how the energy consumption should be reduced then in the following years, which is this dotted gray line. And of course you have to ask yourself what actually happens if we have more renewable energy sources to produce electricity. So is renewable primary energy from renewable sources included in these numbers? And if yes, what happens actually if the share goes up, as we can see in the figure on the right side, that at least according to projections, we'll have a lot more electricity from renewable sources like wind power or solar power, or also biomass. So the question is, what actually happens in our energy consumption? So if I look on an example like solar panels or photovoltaic solar panels, they normally have a technical efficiency, conversion efficiency from the solar radiation into electricity of 10 to 20%. So this would mean if the technical efficiency is included for primary energy accounting, that I would need 5 to 10 megajoules of primary energy to produce 1 megajoule of electricity. And if I assume that the generation from photovoltaic goes up in a country, that would mean that the energy consumption would also go up, because if we use or compared with a fossil power plant with an efficiency of 40%, you would need 2.5 megajoule. And if I replace these kind of power plants with photovoltaic panels, then my energy consumption would go up. If I say, no, the primary energy from renewable energy sources is of course excluded from my primary energy statistics or from primary energy factors, this would mean, in contrast, that the energy consumption goes down, which sounds correct, but on the other side, it does not tell you anything about efficient fuel, but it does not tell you something about the energy efficiency in a country, so how many final energy is consumed, for instance. So this, let us ask ourselves, so what actually is primary energy? And of course there are definitions, and most are similar, one from Nakicinovic. And in this definition, primary energy is, for instance, the chemical energy embodied in fossil fuels, so biomass. This sounds very logic, and I think that this is clear. So it's basically the natural, the calorific content of a fuel. But it's also the potential energy of a water reservoir, it's the electromagnetic energy of solar and wind. So this and combustible fuel. So we use the famous primary energy factors, which express how many how many primary energy I need to produce a unit of electricity or heat. So if we look on combustible fuels, it is basically the calorific value of a fuel multiplied by the input for a certain time divided by the output. And this is nothing else than the reciprocal of the thermal power plant efficiency. So this is normally very easy to calculate the efficiency or the primary energy factor. For a fossil power plant, you normally know what is the calorific value of your fuel. You measure the input, and you also measure the electricity output. So primary energy factor calculation for fossil or combustible fuels is straightforward. So there's no problem to do so. If we look on non-combustible fuels, it's basically the same history, so it's input divided by output. But the problem here is that we measure the electricity output from, for example, a wind converter, or wind generator, wind turbine, but the energy input, so this is not, of course, not measured. And if I want to express the primary energy factor, I have to assume something, or I have to calculate something. What is the input of primary energy here? So let us go to several options we have. So first of all, we could say one option is to not account primary energy if we have renewable energy sources like hydro, solar, wind, or biomass. So we could say, per definition, my primary energy factor is always 0. So I don't need any primary energy to produce electricity or heat. In practice, this is rarely done. It's sometimes done for some energy which is recovered from residues like landfill gas or sewage gas, but normally this is not done. Then the next option is to say, okay, I have to calculate based on assumptions, or in practice it's called primary energy equivalence, which is basically a kind of conversion efficiency. I calculate my primary energy input. And there's no distinction between, in these methods, between non-renewable primary energy and renewable primary energy. So it's basically primary energy from fossil fuels added up with primary energy from renewable sources to one figure. And these kind of primary energy equivalent methods are used for energy statistics normally. And then there's another two options where the primary energy is split up into non-renewable primary energy and renewable primary energy. The advantage is, of course, that I can better distinguish between the infinite energy sources. And this is often done in life cycle assessments, for instance, or environmental assessments, rather not in energy statistics. So in here I have two options. I consider only the non-renewable primary energy. So for renewables, this is of course only the infrastructure then. So we have already this kind of life cycle approach here. Or I have a combination, let's say, of option 2 and 3, which is non-renewable primary energy, which I have for the renewables only for infrastructure. And then again, the kind of primary energy equivalents or technical conversion factors to determine the primary energy input to produce actually the electricity. So as an overview, what I have is I have different options. and for these options I have different methodologies to account the primary energy. So as I said, option 1 is rarely used, and I also don't need any methodology because I simply define that the primary energy input from wind power, hydropower, or photovoltaics is 0. So, but this, yeah, we can more leave left off because it's not used. Then for option 2, which is used in energy statistics, I have 3 different methods which are commonly used. I have the direct equivalence method, which is used by UN energy statistics. We have the physical energy content method, which is used by the International Energy Agency and by Eurostat and OECD statistics. We have the substitution method used by the US Energy Information Administration. And you can already see that there are a lot of different methods depending on institutions or regions. And you can also see in literature that when energy consumption, global energy consumption is compared, that these 3 different methods will result in different consumption numbers. So, and for option 3, there's also no accounting method required for the conversion itself, because for the renewables there's no primary energy accounted, so no renewable energy accounted. So it's a little bit similar like option 1, but we have these infrastructure included, so we would need kind of primary energy factors from a life cycle database. And then for option 4, for the conversion itself, what is used normally is technical conversion efficiencies, or also the physical energy content method, or similar concepts. And then also for the supply of the infrastructure, also kind of life cycle assessment factors.
Great, excellent. So yeah, maybe just to hold on for a second. So what we learned so far is that we have different types of primary energy. So some distinguish between renewable and non-renewable primary energy. Others go with a total value for primary energy, and we heard about the different options. But what actually is calculated is following some methods. And so the question would be, how does this calculation look like? So how are the differences between the methods? Can you maybe a little bit elaborate on that, Alex?
Yeah, sure, Oliver. So if we go on with the accounting methods which are used in energy statistics, so the first one is the direct equivalent method used by UN statistics, and it's basically very simple. What they assume is simply that there's a primary energy equivalent or conversion efficiency of 100% between the ingoing primary energy and the electricity or heat output. So this is valid for non-combustible renewable sources, or renewable and nuclear, but it's important to say that it's only for non-combustibles. So for combustible, it's all statistics use the same approach as I have already shown before. So this is focusing now on the non-combustible fuels here, energy sources. So as an example, I have the wind generator here. So if I produce 1 megajoule of electricity from a wind generator, the direct equivalent method says that I have consumed 1 megajoule of primary energy, and it is the same for all other non-combustible sources like solar power, hydropower, and also for nuclear and geothermal. For biomass, as I said, it's different because it's a combustible fuel, so it's handled like coal or natural gas in the primary energy accounting, so they look on the calorific value. So this is the first one, the direct equivalent method. Then the next one is the physical energy content method used by Eurostat and the International Energy Agency, and also other OECD statistics. Here what is important is already the definition for primary energy, and it says that it should be the first energy from downstream in the production processes for which multiple energy uses are practical. So I have one example here. The first example is solar thermal, so not photovoltaic, so solar thermal, and of course you can produce, the solar radiation is used to produce a kind of heat, and this heat can be used to produce then electricity or steam or thermal energy. So the heat, after the definition of the IEA, is the first source or energy for which you have multiple practical uses. And this means that the heat, the produced heat from solar radiation, is the primary energy. And then the IEA has introduced, and Orista together with IEA has introduced kind of efficiency or primary energy equivalents, and for the steam or thermal energy generation, this is 50%. So this means that you would need 2 megajoule of primary energy to produce 1 megajoule of steam. And for the electricity production, for instance, in a concentrated solar power plant, the efficiency assumed is 33%, and this would mean that you need 3 megajoule of primary energy for 1 megajoule of electricity. And this is also how they account primary energy in their statistics. So they look on how many electricity is produced from a concentrated solar power plant, and then they multiply it by 3, and they know how many primary energy is consumed. Then I have a second example within the physical energy content method. It's for wind, hydro, and power and photovoltaic. If you think I have a wind converter, and there comes wind or kinetic energy in form of wind, and it passes my wind turbine, and then the generator produces electricity. So there is no, though electricity is the first energy where I have multiple uses. So with the wind I cannot really do other things. I cannot power a car, for instance, with the wind directly, maybe a ship, but so this is not really counted here. The electricity from wind or hydro and photovoltaic is the first energy with multiple uses. And this is why for wind power, hydropower, and photovoltaic power, I need 1 megajoule primary energy to produce 1 megajoule of electricity. So the third method is the substitution method. It's used by the US Energy Information Administration, so the EIA. And what they use is the technical conversion efficiency of the fossil power plants which were substituted or that would be needed to replace the electricity from renewables. So if we think for European power plants, the average fossil power plant efficiency, so coal, natural gas, fuel oil, is roughly 40%. So all electricity which is produced from non-combustible renewable energy sources will have this 4% primary energy equivalent, which means that you would need 2.5 megajoule of primary energy to produce then 1 megajoule of electricity. So for every megajoule of electricity from wind, from hydro, from solar, the EIA accounts 2.5 megajoule, or would account 2.5 megajoule primary energy if they do the would do the energy statistics for Europe. So for the US, the average efficiency might be a little bit different. And then finally, we have the technical conversion efficiencies. So what the technical conversion efficiency does is basically that looks on how many primary energy in form of radiation will go onto a photovoltaic panel and how many electricity is at the end produced. So for hydro, it's the same. What is the potential energy in water, which is more or less defined by the water height, and then based on this efficiency, I can then calculate the input of primary energy. So in case of hydropower, it's roughly 85%. If we look on photovoltaic panels, it's, as I said already at the beginning, 10 to 20%, depending on the type of technology which is used. So you see already that there are, of course, different numbers and also different types of what is accounted here. And as I said already before, this is often used in environmental assessments, so such as life cycle assessment, for instance, but it's not used in energy statistics.
Wow, yeah. Thanks, Alex, so far. I think we got a first flavor introducing the different methods and the concepts behind that. These will most likely lead to different results if you look, for instance, at single energy carrier supply chains, but also maybe looking at country average grid mixes. So that would be my next question. So how does it look in practice? I mean, we heard a lot about the poor theory and that there are different concepts applied by different institutions, but in the end, what counts are the numbers, and how does it look like? Did you have some examples to present today?
Yes, of course, I have some examples here. So what you see is basically the primary energy equivalents or conversion efficiency, which are used in the different methods for non-combustible renewables, and I also added here biomass as an additional example to see how different it can be. If you look on hydro, so the direct equivalent method and the physical energy content both result in 100% energy equivalent. So it means you need 1 megajoule of primary energy to produce 1 megajoule of electricity. The substitution method is for all energy sources around 40% here, and then you see technical conversion efficiency of 85. So you already see for hydropower there can be already very different numbers according to the energy statistics you use. So if I would have, let's say, the energy, I want to calculate the energy consumption in a country which is mostly or uses electricity mostly from hydropower, like in Norway, then with the substitution method, there would be a lot higher primary energy consumption than for this country than for a direct equivalent method or physical energy content method. For wind, it's very similar to hydro, and it becomes very interesting then for instance, for solar thermal electric, you see that there are very different conversion efficiencies of primary energy equivalents according to the different methods, and then for geothermal it gets even more diverse. So if I compare between direct equivalent method and physical energy content, you see already that there's a factor of 10. So as long as geothermal is not really used, it does not really matter, but there are certainly countries with a higher share of geothermal for electricity production, and then you see that if I'm not aware of the different methods, then there can be, of course, I can see very different numbers. So for biomass, of course, for all methods, I have the same conversion efficiency because it's done like for a normal fossil power plant. If I convert this to primary energy factors then, which is more or less the reciprocal of the conversion efficiencies, I see that for option 2, which is basically the energy statistics with the different methods, I see already how different it can be. So how many primary energy I account for a megajoule of electricity or heat produced. Or in this case, it's only electricity. So if I assume, for instance, I have a country which has 100% of electricity or energy consumption from geothermal, then for if I use my direct equivalent, then it's 10 times less energy consumption than with the physical energy content, and it's still the same energy source. So you see that this is really important to consider that these different methods can result in very different numbers, especially if I look on a very specific case. So if I look on the average, this is maybe not the case, but for very specific countries, also for the future when we have more renewables, this can really can result in very different numbers here. So for option 3, basically there's only the infrastructure included, so the numbers are rather small. If I look on option 4, which is used in life cycle assessment, you see the advantage a little bit that the primary energy is split up here into non-renewable and renewable, because here it is still easy to understand because it's just one specific energy source. But later you will see that, on the next slide you will see that when I go to country-specific grid mixes and then primary energy factors for a country, then it's not so easy anymore to understand why these numbers are like they are. So if I go on to primary energy factors for country-specific grid mixes, we have chosen some grid mixes, nice grid mixes of different countries. So we have Norway with a very high share of hydropower, 95%. Then we have Poland with 88% of coal and a little bit of renewables and natural gas. And then we have Spain with a very diverse mix. So there's nuclear 20%, coal 10%, natural gas 30%, we have 15% wind and hydro each. So these numbers refer to 2010. So if I look then on my primary energy factors, what I see is that for Poland, of course, the numbers are very similar, which is clear because for the fossil fuels like the coal, all methods are more or less the same. What I see here for option 4 is, for instance, that I have in addition a little bit more which comes from the supply of the fuels, from infrastructure. So this is why it sums up to a little bit more than 3. But it's very similar. It's for most 3 megajoule per megajoule of electricity, and you see that as long as you don't have renewable or high share of renewable energy sources in your grid mix, then it doesn't really matter. But if I go then to countries with a high share of renewables or a very diverse mix, then you see that it can really produce different primary energy factors. So if I look on Norway, with the direct equivalent or the physical energy content method, I have 1.2, and it's a little bit more than 1 because you have 5% natural gas and you have some grid losses, so that's why it is a little bit more. And if I look for an option 4, the technical conversion efficiency, it's also very similar, 1.3, because there's conversion efficiency is 85% plus a little bit of non-renewable, which comes from the natural gas and infrastructure, so in total it's 1.4. But if I look on the substitution, and I see already that then I have a different number here. So Norway has basically natural gas, so that's why the efficiency is relatively high then. But you already see that even with this high efficiency, you will have more or less 50% more than with the direct equivalent or the physical energy content. And if you look on Spain, it's definitely the case that it's very difficult to understand the numbers because of this very diverse mix of energy sources. So we have 1.7 in the direct equivalent method and 2.5 in the substitution, so there's already a big difference. If you look on the technical conversion efficiency, you see that where you see the split up of non-renewable and renewable, you understand a little bit better that there's a lot of renewables already included. Um, but as I said, it's very, very difficult to understand these differences between the different methods if you don't really understand how they work. Yeah. Um, and then there's one final point for the country-specific grid mixes is that in the energy statistics, when you import electricity from another country, this is always accounted as with a primary energy factor of 1. So it means that if you're a rather small country, this can really change your primary energy accounting. Because when you import a lot, or you will import more in the future because of the renewables and the fluctuations, then the imported electricity is accounted with a primary energy factor of 1. So that's, at least for, if you just look on the statistic, that's a way of bringing down your energy consumption. You just import the energy, the electricity, which is of course not a meaningful solution, but if you just look on the statistic, that would be a way. So therefore, this is also something which you should have or keep in mind if you look on primary energy factors for different countries or energy statistics, that this can play a role here. And as I said, it's rather for smaller countries, or maybe in the future when we have higher fluctuations, especially if you look on Europe, we have some countries where a lot of electricity is transferred. So like Switzerland or Austria, which have a very high share of imports in the supply, but they also export a lot of electricity. But if you just look on the energy statistics, then this can lead to some distortions.
Okay, wow, very interesting results to see all the different numbers by applying the different accounting method. So I would assume that quantifying the primary energy of the renewable energy carriers can lead to these completely different results. So in the end, it probably makes it quite complicated when looking at the different statistics and comparing numbers or deriving targets, or maybe even trying to set new targets, if these results can be so different. So Alex, what would be your recommendation or your conclusion, the lessons learned out of the studies and looking at the numbers, how this can be treated?
Yeah. So the first conclusion is certainly a kind of a summary here, that we keep in mind that there are different definitions of primary energy, that primary energy can be accounted in different types of primary energy, let's say. So we have sometimes total primary energy, which is mostly used in the energy statistics, but we also have applications where people split up primary energy in non-renewable and renewable primary energy. And then for the non-combustible energy sources, it is very important to understand that mostly we use not real efficiencies, which also have constraints, of course, but we use kind of methods which try to calculate the primary energy, and there are different methods out used from different institutions. So if you always work with one institution or just look on one region, like we always use Eurostat in Europe, then it is not so, the problems you might face are not so big, but if you even compare statistics or numbers from IEA and EIA, so then you're already in trouble. So this is especially important to keep in mind that there are different methods out. So this as a summary, and then for the conclusions, I think it is, we have seen that depending on the methodology and the type of primary primary energy, there can be very different primary energy factors for the same renewable energy source. So if I don't define how it should be calculated, people can, when they choose different methods, they can result very different results. And of course, at the end, I will choose the method which will give me the best results. Yes, if I want to express the advantage of a system or the how I fulfilled a certain target. So there should be some, of course, rules how these primary energy factors should be calculated. We personally, as we have a focus on life cycle assessment, believe that a split into renewable and non-renewable primary energy could help to interpret the energy consumption of time or to understand primary energy factors. Because finite energy sources are not added with infinite ones, so this is an important thing. But I know that, especially in energy statistics, that this is sometimes a little bit too complicated. And then finally, if we look on primary energy factors and energy statistics or targets, and we analyze them, and we want to make a policy or we want to make conclusions, I think it is very important to compare or to analyze these numbers with care. So we have to ask ourselves, is this the same methodology? What actually happens when we have increasing renewables and electricity imports? So what is the impact on my methodology? What is the impact on my primary energy factor or my energy statistics? So I should at least understand what will happen. And then finally, we should also ask ourselves, is primary energy always a helpful indicator for a target? So if we talk about houses, for instance, I can of course calculate the primary energy factor, but it does not tell me anything about maybe the efficiency of my house, or how many final energy is consumed in my house, so how many electricity or how many thermal energy. So if I just look on my primary energy factors, this might mislead me. So I think these are the main conclusions, and to give you an outlook for the second part, this is also what Andreas Helmling, Ecofist, will then further work on. So he will focus in some case studies what actually happens if I apply different methodologies for primary energy factor calculating and apply them these methods then, and what happens then. So there are sometimes extreme case studies, but it's very useful to show what happens actually if I use these different methods, and this also reflects then the primary energy factor or primary energy use in different EU directives or communications or targets. So yeah, so thank you for your attention, and I hope you will also join then for the second part from Andreas Helmling then in about 2 weeks. So I think that will be also very interesting. So thank you very much.